Okay, so let's start the day 2 of the Intro to MATLAB class. Okay. If something is getting stuck. Okay. So yesterday we essentially went through vocabulary. We went through a lot of information, how to write statements, how to communicate with MATLAB. It was mostly syntax, how to write different types of expressions, how to store data in variables, how to retrieve them. And today we'll try to use this information to look at the real data extracted from one of the papers, just to explain you where the data is coming from. The paper is from about 10 years ago. It's essentially describing a set of experiments where these cells were modified by knocking out one gene at a time. Okay, and then for each variant, each mutant, each modified yeast line, the authors measured the expression of the genes there. Okay, and they report for one experiment at a time. In columns, we've got individual experiments, each one corresponding to knocking out one of the genes. Okay, so there's bunch of those, about 700 or so. And for each modified yeast strain, the authors measured what is the expression level of the genes that are still there, and they report the data for about 3,000 or so different genes, and the way they do it is pretty conventional. Typically, in the type of experiments, you report what was the ratio of the expression in a modified organism relative to your reference unmodified strain. Okay, and if you want to see what's the change in expression level, typically you report it as a log of the ratio. The idea is that if the log ratio is higher than 1, you've got overexpression. More of the gene is expressed in a given experiment than in a wild type. If log level is below 1, it's negative. It means that that expression dropped. This is pretty conventional. Sometimes the log is sometimes the log base 2, sometimes it's log 10, but typically data is provided as a log ratio table. Okay, and I just took a file that's provided as a supplement to this paper and uploaded it into our Google Drive, and that's what we're gonna use later on. That's us today. All the PowerPoint slides that I'm gonna show, the rest of the slides can be used just as a reference for different things that we'll go over today. So I think it's better to go through the actual MATLAB operations instead of showing static pictures. So let's get out of PowerPoint. Okay. And let's go to MATLAB. Okay. So let's make it bigger, and I've uploaded into my current folder, into the folder that I'm working in, the files that came from the Google Drive. This is the current file we're gonna go over, okay, with the scripts, and then apart from that, there's the paper I took the data from and a few data files that are based on the on files provided by the authors. Okay, but before going there, let's recap what we did yesterday at the very end. Okay, let me clean my command window and my workspace. Okay, so we don't have anything here, and the very last time yesterday we generated essentially a file with the simulated data. That's right. Those are the blocks, the sections that I pasted in from the yesterday's session. Okay, the block here, the section here, generates our data. Okay, we can run it once more. Control Enter is gonna run this particular section of code. We're gonna see what it generated, and this is our data sitting in a 1000 by row times 10 columns array, or matrix if you prefer. And to save this data, we can run another block of code. Okay, Control Enter is gonna run it, and we wrote the data out. Okay, and if we look how the file looks like, this is our test data 1 tab. This is the file here. If we open it outside MATLAB, let's open as text. This is essentially tab separated file with a bunch of numbers, and this is very typical. A lot of data that you're going to be reading into MATLAB, data that's provided with different articles looks like, and also data that you generate in-house also looks like that. So MATLAB's got no problems reading this thing. If we read the file, another block and Control and then Enter, we can read it back. The original data was created in a myData variable. Whatever we read back in is named TD1, because this is how I imported data from the file. Okay. Are those two pieces of data the same? They should be. That's right. We just wrote myData variable to a hard drive, and then we retrieved it back. So they should be different, identical. How to check it? It's relatively simple, right? We can, for example, subtract each value in myData variable from corresponding value in a TD1, and if the data is identical, the differences should be close to 0. Okay, isn't the case? Well, we can always try. We can first generate we can make first a block, let's say here a section, so that we can run it on its own. We can look for a difference. Let's say it's called diff. I'm selecting diff. No. Diff. Okay, and we're gonna subtract my data from TD1. Okay, this way And this is gonna be happening according to the rules of subtraction of matrices, which means it's gonna be done element by element. Element 1, 1 in TD. In my data is gonna be subtracted from TD. One data at position 1, 1, the value at my data sitting at fifth column and 37th row is going to be subtracted for a corresponding position, and those things should be pretty close to 0. Let's see if that's the case. To check it, we can run the block. Okay, we do have now our difference. How to check? Well, we can check one data point to see if there's hope. That's right. We can check, let's say, T diff 1, 1. This is our first position there. What do we have there? Oh, this is not, no, because I got the typo. And it's T D diff here. Yes, and this is close to 0. It is not exactly 0 because we lost precision when we wrote data to this file. When writing data, we specified as a format floating point number with a 3 decimal points. Apparently, whatever was sitting in my data at this position had more digits than after decimal point than 3. So this is what we lost, and this is on the order of 10 to minus 4th. So this is fourth digit that's missing. So those things are fine. So our first position is fine. We retrieved it with as much accuracy as we can. What about others? Well, we can try to use of the functions we introduced yesterday. Let's say function called max. Okay, and I'm gonna write stuff to somewhere else. Let's call it dmax. I'm gonna write data to dmax, and I'm gonna get a max of my variable is apparently td diff. Okay, so I write it there. And what do we get? This is gonna be the largest value. Here's the result somewhere. Well, this is a lot of numbers. Each one is corresponding to what? Well, we can check size of the max, and we got 10. We've got an array with 10 values. This is because with no other parameters but an array, max is going to return you maximum value calculated for each column. This is, or across rows if you prefer. This is default behavior of a max function. If you want to check the overall maximum value for the entire matrix, you can run this, use the same function, but what you do is you specify that you want all values. If I'm correct, this time I'm gonna just write this thing out. No, nothing. Well, maybe. Well, if it doesn't work, we can always ask for help. Right? Let's see. Well, let's try to ask for help. This is perfectly fine. Let me just can't see Okay, here let's say MATLAB max function, and we can check the help. What do they tell us? Well, if we want to look for all elements in an array, we've got to use a dummy argument before all. The reason is that there is a variant of the function that can be used to find maximum value when comparing to when using two arrays. You can feed it with two arrays, and then the max function is gonna return you the bigger value of the one sitting at in array 1 versus array 2. So that's why there's this dummy argument here. Okay, so let's rerun our max function, but in a slightly different way. Okay, we've got to provide an empty argument here. This is just an array with no values. Okay, and then once we run this, well, nothing comes out because I do have a semicolon here. The result is still stored in a variable called ans, answer, and this is indeed something on the order of 10 to minus 4th. So this is the largest errors that we are able to get when writing a number with several several digits after decimal point, but we wrote only 3 of those. The error is going to be on the order 10 to minus 4th, so that's perfectly fine. Okay, so it means our procedure works. We're able to like quick check that our code is doing whatever is expected of it. Okay, so now how to check what's there. Okay, we're getting those arrays with numbers, and well, we can as before, we can characterize what's in the table by calculating things like our max or maximum of each column. That's right. This is what we've read in, so we can calculate that. Oh, and we've got typo somewhere here. Yes. Okay. Function, and this is, well, I've got still a typo. I'm clearly dyslexic. Okay, so we can try. This is my TD1. This is this one, and we can see it. If there's no semicolon, you're gonna see the output in the command window. If semicolon is there, the printout is pressed. So if we don't use it here, this is maximum for the entire array. This is if we skip the arguments. We're max all the arguments. Those are the maximum values for each column. If we want to do the same thing going row by row, we've got to change direction. So we've got to, instead of averaging along the first dimension, this is equivalent of what we just did, presumably. We're calculating averages of the TD array along the first dimension, so along rows. So that's why we're getting average of all, I mean the maximum value for the first column, because we looked for maximum along the first column, then along the second, and so forth. So across the, if you want to change direction, then we're gonna go and look for maximums in each column. There's gonna be a lot of columns, thousands of those. So I'm gonna write this thing Cmax to a variable, so I don't clutter my command window. Okay, so this time the results go to Cmax, and this is what we've got here. And we can look for a fragment of it by, let's say, looking at Cmax and saying we want to look at the position 1 to position 10, let's say, and see the values here. So those are the 10 first rows, and for each row we've got the maximum value showing up in there. So that's how to look at the numbers in your array directly, or that's how to look at some parameter, some property that characterizes the contents of individual columns or rows. The thing is, it's not very informative. It would be much nicer to look at the data. And to do this, we can just start with a workspace, okay? And if we go under the variable we're interested in and the right click, a number of options show up. One of them is deleting the variable if we want to, one variable at a time, but we can also plot it. Okay, let's see what happens. Okay, I click on plot, and hopefully, if nothing bad happens, we do have a plot. I'm gonna get rid of the help thing. That's just an XY plot. The horizontal line goes from 0 to 1000 because we've got 1000 rows in our array, okay, and each column is gonna be plotted as a separate trace. It does have 1000 values, and then the value for this column one at a time is going to be plotted as a line. This is sort of cluttered because we've got 10 of those overlaid over each other. So this is sort of messy. So instead of looking at the entire array, we can look at one column at a time. This got to be done from the command window, because here if we look at the plot, we're gonna see everything overlaid on top of each other. Luckily, we do see what happened when I selected plot here. Then what's actually happened is the command that looks like that got executed in a command window, so I can reuse this thing. Okay, but instead of plotting entire TD1 array, I can say I want to look at the column number 1. That's right. This is my array. I'm picking all the rows, but just first column. Let's see what happens here. Well, let's go here. And hopefully, if I pull the window up, now we've got only one trace showing up. So this is a quick way of checking if whatever is in our array is actually whatever we expect, right? This is one way of looking at the data. If we want to look at another column, we can look at the, let's say, last column. We had 10 of those, so we will plot. Here's a 10, that one. Looks very similar. It goes from 0 or from 1 actually to 1000. Those are our points in 10th column. The values go between somewhere minus 30 or so to plus 30. This is different if you're careful. You might have noticed that it's different than whatever we had here. Whatever we had here, if we check the first column, we're going somewhere between -3 and 3. And this is also consistent with the way we generated our data, right? If we go back to the code here, we were modifying the width of the normal distribution that the data was drawn from. And we started, first column was 1 unit wide, the last column was 10 units wide. This is what generated our data here. So each column of numbers corresponds to wider and wider distribution of data points. We can see how wide it is by, instead of looking at a plot of the data, we can look at the histogram, okay, of the same array. If we click on histogram now, what we've got here is we're getting histogram of all the data points of the values in the array. But the thing to notice is that histogram is working slightly different way than plot function. Plot function was if fed with an array, plotted each column of data as a separate line. Histogram is taking all the data points in an array by default and plots them on one histogram. If we want to look at the one column at the time, we've got to do the same thing as what we did with plot. Instead of using TD1 as our input, we're gonna go and take entire column at position 1. Okay, and then if we run this thing and pull the window up, here come on, hiding with the zoom. Here's our default version of histogram for the data sitting in the first column of our array. Okay. If we can do the same thing with and now, the thing to notice is that this is roughly spanning the range between -3 and 3. Okay, if we do the same thing but check column 10 and check what's here, it's somewhere between 30 and 30. Why is that? Well, the normal distribution is expected to have most of the values between its width, half width, which is 1 by default. So if we go back to our distribution here, what we've got is most of the data falls between the -1 and 1. If we go to twice the width, we should have about 95% or so of data falling in between there. So that's right. And if we go to 3 widths, most of the data, like 99% or so, should fall in there. So So that's why the width of our first column is 3 plus minus 3, whereas the 10th column is 10 times wider, goes from minus 30 to 30. So that's sort of sort of informative. Also confirms that our data that we generated looks as it should look like, right? So that's way to cross-validate. If we don't like the way the histogram looks like, we can modify it. I'll go tomorrow over how to do this through the GUI and how to make this thing nicer and how to modify it in an interactive way. But today we'll try to do it within a script. To do this thing, instead of calling histogram like this, we can actually assign whatever it's returning a variable. Let's call it this. H10 is gonna be histogram 10. Okay, and then we're gonna get the histogram back. But we also do have a variable here. If we check what's in H10, it's gonna return us a number of properties that we can modify. This is information about what's in a histogram, but it's also allows us to modify it. Let's say if we want to change the width of the bins for the histogram, we can say that we want to set the property called bin width of the histogram to, let's say, instead of default 3, let's make it 1. Okay, and if we set bin, and if we set it, now if we look at the histogram, now each bar, instead of being initially 3 units wide, is just 1 unit wide. So this returns us finer grained information about distribution. We can also modify what's shown on the vertical axis. By default, we're getting just counts of observations within each bin. So let's say in the center we're getting about 2 bars with about 45 observations there. This is useful when looking at a single series of data. If we want to compare several of those and they are not of the same size, one might be 1,000 observations, other 2,000, another one. Then we, instead of looking at the counts, we might want to look at we might want to look at the probability, how likely it is that we observe a value at between -1 and 1 versus 27 to 28. To change this, we can modify the normalization count here. This is another property. Let's check H10 and do normalization, and let's change it from count to probability. Okay, and if we change the setting here, and then if we go here, now we're getting a number corresponding to the fraction of observations falling within each of the bins. The total, the sum of the values in each bin should add up to 1. That's how how probability is defined, the total probability over all the cases should add up to 1. So that's another way of the normalizing thing. And then if we so now we compensated for the differences in the number of observations. We'll still do have to deal with situation where some of the histograms are one unit wide and another 2 units wide and so forth. So we can also compensate for that by calculating the value which actually is telling us, getting us a number that's independent of the histogram width. This is probability distribution, I think, function. That's the name of the value. Let's see, prob PDF is it? I think, and then if we go here, no, is it PDF? No. Yeah, probably PDF. I think that's it. That's it. Yes. Okay. It didn't change. If I'm correct, it didn't change because our default width of a histogram bin is 1. I mean, default whatever we set is 1. But if we change it, let's say, let's change the width back to 3, and let's see what happens here. Well, we still are getting a number that was similar to what's before. This is the height of the histogram normalized to probability density function. So it takes care of the width of the sample size in the interval that we generating histogram for. And here once more, this is 3. If we go back to 1, we're still hovering somewhere around 0.04. It's just data becoming more noisy because our sample is relatively small, so the number of counts is relatively small for this particular histogram. Okay, so that's how you can look ad hoc at the data you've got and see if it's sensible. You can check if data is sort of sensible, and in this particular case, the data that we are looking at this moment, the synthetic, it's generated by our script, but in general, it would be something that's coming from experiment or from some data coming from a paper that you might want to look at. Okay. So let's stop for a moment, and if you feel like playing with plotting histograms and plotting things, that's probably a good time to practice. And once more, the only way to learn how to use MATLAB is to play with it. It's the way to get yourself familiar with different options, different settings, and just practice, and that's how it goes. So let's stop recording for a moment. Okay, let's make a break. Let's say for like 5 minutes or so. Okay, pause. Okay, so let's resume, and let's now try to actually read the data that's more typical and the real, something that's coming from experiments, not from playing with the random function generated. Well, I mean, I'm not sure what you mean cannot work directly. Well, it does directly in a sense that, because H10 is the plot itself. You see, H10 is whatever was generated here. Okay. H10 represents the figure that the plot that we had. That's right. You can do the same thing with plot, but then what you do is, let's do it. You would do P10, let's say, for plot of the 10th column, okay, and we'll do plot, and we're gonna plot our TD1, and we're gonna plot entire column at position 1. Okay, and then if we do this, oh, what is it? I've got that. I'm missing. We can plot our TD1 array, the entire column at position 1, and whatever plot returns goes into P1 variable. Okay, we can do it this way. Now we've got the plot of the first column. Those are values in the column starting from first one to the very last one. And what we gained is we now got the P10. If we check what's in P10, now we do have information about different properties of our plot. We can, for example, change the way it's plotted by saying P10, and let's say line width, let's make it let's make it 1. Okay, and then I've got a typo. Line. If we change the line width property, now the lines are wider. So this is the same idea as in case of histogram. It's just that you've got to generate a variable containing information about our plot when it's generated, and then you can use it to modify some of the properties of this particular plot, depending on type of the plot. Is it a line plot as here, or a histogram? You're gonna have different set of properties, right? Whatever we see here for our line plot, it looks different than whatever we've seen here for a histogram. Here we've got the bin width, here we've got the normalization for the histogram. It's not present here because this is a different type of plot, but the idea is the same, that you generate either a line XY drawing or a histogram, and then if you want to modify its properties, you save whatever the function call returns to a variable, and then you can modify it like we've seen, like we've had here to modify the line width, right? So that's the idea how to deal with the histogram. We'll go through more of the details of that tomorrow. Here it's just to have a quick handle on what's in the data we're generating, how to look at the stuff. Okay, so hopefully this answered the question. Okay. Okay, so now what we've got here in my data is artificial. This is synthetic data generated from a script, but we can read something coming from actual papers or experiments. If we do a quick, if we quickly look at this file outside of MATLAB, we'll see what's there. Okay, so this is the original file. No, this is the original file that came from the paper. I just downloaded it from the journal site. Okay, and I'll try to open it in Excel, which should be somewhere around. Okay, let's try. Here's my Excel, and I'm gonna know I don't want recovered files. I just want to open something else, and the something else is sitting in my desktop in W12 directory. I want to see all files. And I want to see this one. Okay, when I open it, then standard Excel fare. We've got to say it's delimited. It's gonna split it correctly into columns, and then you can finish. Here's the data. Okay, it is essentially a huge table. Okay, if we no, this is no, I want the full, no, this is, okay. This is the one that I prepared, but I wanted to actually open. Oh hell. Oh, shoot. Escape. Okay, something bad happened. Okay. Here's the file open. Let's close it. I think my laptop is getting unhappy. Still sharing. Yes, I'm still sharing. Okay, let's go back to Excel. Okay, let's go back here and then open other workbooks, go to browse, go to desktop, go to W12, look at all files, and let's get the full file. Okay, let's open it here and then we finish it. And should find the data file. Okay, so here's the entire file. It's essentially a block of numbers, right? Here are the rows and columns with the numerical data. It goes all the way to about 700 or so positions. Each one corresponds to one of the genes deleted from a knocked out in a cell line, and then for each of those strains, there's a measurement of the expression level for individual genes reported as a log ratio. So this is, I'm not sure if it's log 2 or log 10, but it's otherwise log ratio. If the number is positive, it means expression went up. If the number is negative, expression went down. And there's one set of numbers for deletion of STB4, then for 13, and so forth. Now, this is sort of cluttered. There's a lot of text columns. So to make the file simpler, I just cut out the file with the part of the spreadsheet with the numbers and left annotation of the experiments in the first line in the header, and then the information about the gene in the left two columns. So the file that we're gonna look at is actually this one. And if we open it, it's essentially the same numerical values, but only with one column corresponding to the header with the genes that were deleted and genes that the expression level was measured. So that's what we're gonna read, and let's see what happens. Okay, I'm gonna kill Excel so that it doesn't take us too much space. Let's go back to our Excel, and this is our file that I was just looking a moment ago. Okay, when I run this block, okay, caused by out of memory, we've got a memory problem. So let's clear the workspace. Okay, and let's see if we can run it now. Control Enter, and do we have any hope? Oh. Well, it's still out of memory. Is it really the case? That would be bad. If this is the case, that's try once more. This is not expected. Let's do Control Enter once more. That's really the case. Clear command window, clear workspace, and let's try once more. See what happens. Control Enter. Yeah, if this is the case, well, we'll have to trim the data so that it fits. We can work with it. So let's make the table smaller. To do this thing, well, we're gonna go back to the light here. Go back. Let's go back to Excel. Okay. Next down. So let's go back to Excel. Let's open our smaller data set. Okay. Let's see how to do it. Let's go to, well, maybe let's pick up a few things here. Okay, let's select maybe. Okay. Let's go to the very end. Okay, let's remove all the stuff here. This is unexpected. I thought this laptop can handle it. Apparently it can. So let's just delete what we've got here. Okay, so now we've got a much smaller file. That's the problem when we're working with the laptop. So let's now file, save it as, and let's call it no. Okay, and now let's still tab delimited. Let's save it. Yes. Let's now file and create. Okay, and then don't save. Okay, so now let's see if MATLAB can deal with it. Okay, so instead of reading the file here, we read small. And let's see if it's happier. Control, enter. Okay, now it's much happier. We're able to get 130 or so codes in. Okay, but if we check what's there, well, if we read our initial data set, let's reread the reread the data file here, control here. Once we read our test data file, this was file only with the numbers in and nothing else. The result was I want to read it here. Control, enter. The result was my TD1. What's the problem? It's not reading. It's data control. Let's see. Clear data. Okay, let's try to control. What is this? Opens next. Oh, lost test data 1. Why is it? Well, we can generate it back. Let's run this piece of code over size along something. There's a typo here, line 20R. Open. Oh, because I lost whatever I had here. I lost my data. So I cleaned the workspace. That's the problem. So let's go back and do Control Enter. So now the data is generated. Now we're gonna control and save it. Okay. So now we should have it there, and then we're gonna read it. Control enter, and here's our TD1 data read from a file only with the numbers. We ended up with an array. That's what the workspace is telling us. We've got an array with 1,000 columns, 10 rows. Okay, but what came out of reading our data file with annotated with the gene names and whatnot, we ended up with the variable e that's here, and this is something that's annotated in different ways. It says 1 by 1 something. Okay, if we check what's in e, it turns out that this is not an array. We ended up with something called a structure with 2 fields. This is a more complex data structure used to store different types of information of different types. And it's composed of 2 pieces. There's a piece called data, which looks like our array with numbers. Plus, there's another element called text data that is similar in size, but contains something called cells. Well, to access each of those things, the code is just assigning what's in the data to a one variable, okay, which I then copy to something called ed, because I'm lazy. I want to type this text thing. Okay, darn it, 8 my variable e data. That's what I had here. Sorry, I had that one. No, I had the export here. Expression. That's what I've got here. Okay, this thing here. Okay, and then the text data goes to a text, and then I copy it to ET because I'm lazy. Okay, so let's run this piece of code to have ET and ED there. Okay, what's in ED? If we check in the data, if we check size of ED, okay, it's 3,000 or so rows. Those are going to be rows corresponding to different genes that the expression for them was checked, and 136 columns of data, each one corresponding to a separate experiment. If we check the first few elements there, well, we can say ED, let's say 1 to 5. So we're gonna check 5 rows, and we're gonna check for those first 5 columns. So if we check what's there, we've got to use round brackets, not square ones. If we check what's there, yeah, we've got the numbers coming from our table. What's in the ET? What's in this text data? Well, we can try and do the same thing as before, but we're gonna use ET. This is where our text data ended up in. And what we see here is we see that this is where the text from the annotation of the columns and rows came from. The first 2 columns contain the formal name of the gene in yeast, so that's the ORF column. This is the, and then we're getting gene names. Then there's a standard name of the gene coming in the second column, and then at the top of the table we had genes that were deleted in a given experiment. So those are the fields filled up with text. What's left, most of the bulk of this this matrix, this is an array, is with fields that are empty, and the values there that you see there are something called cells. This is the way, one of the ways that MATLAB is using to represent strings that are not supposed to be treated as an array. If this is how the data is gonna come in from the files that you're reading with the import data. There's a few slides about this thing in the PowerPoint. I don't want to go into how this thing is working. If your data files contain a lot of text that you want to analyze, it's probably better to use something else that MATLAB is better dealing with numbers with and staying with bare minimum dealing with text. This is probably better. So extraction of the data from files that are mix of numbers and text is more complicated, but at the very end we did ended up with an array here, this one that contains our expression data that we're interested in. Okay, so what to do with those numbers? Well, we can do the same things as we did with our artificial data. That's right. We can try to find the maximum value in each each column of row, minimum value, average, the variability, the standard deviation, and that's how we can deal with the data. Here it's gonna look less regular than we had before. Let's try histogram, and let's take our TD. Let's get our, what was it? It was our ED. Let's take histogram for one of the experiments. So let's take one column, and let's take the first experiment, whatever it is. Right, and I need another bracket here, and here is a data that's corresponding to changes in expression level for 3,000 or so genes upon removal of the first of the genes that were knocked out in the first experiment. Right, this is the one. So this is one of the experiments. We can check another experiment, let's say at position 2. Okay, let's try it. Here's another one. The histogram looks skinny because there are apparently things somewhere here that are very small. There's a very small number of data points with a very high expression level that are plotted. We don't see them, but they are there. Okay, we can check another histogram, but now we can go across a long column. So let's try the first gene on our list, and let's see how expression of this gene changes across different experiments. So this means we're taking the first row of the table here, but we're going across all the columns, and we're plotting values there. Okay, and here we've got only 100 or so data points, so histogram is more coarse-grained, but it's similar case. We've got a lot of conditions where expression is not changing that much, and then we've got few genes that got expression up much more. So this is how you can check what's in your data in a very rapid way, just to evaluate what's there. The tricky part is trying to find things that are interesting, right? Because so far we've got a bunch of numbers and checking each column, each experiment by hand. When you've got a couple hundred of those things, it's not feasible. So you've got to do something. You'd like to automate this thing. So we'll try to see how to find interesting things in your data, and how MATLAB is helping you to do this thing. Let's see. So okay, well, we can redo this thing. Okay, so let's go back. Let's go back to our first column and bunch of data there. Here we go. If you look carefully, there's also data scattered all over here. Those are things that are interesting, right? Because those are genes that got their expression modified when you knocked out one gene in yeast. That's right. Most of the genes did nothing. 0 means there's no change. This is log log ratio of the expression data. So if the value is 0, it means that for a given gene expression is the same in our knockout versus the wild type. So there's nothing happening. The gene doesn't care if something got done to waste. The interesting things are either with corresponding to high log ratio values or low, because those are genes that change their expression upon removal of some other gene. So there might be some functional connection between the gene you knocked out and those things that got their expression changed. So those are things that we're after. How to find them? That's the point. You can do it if you've got 2 knockouts and 10 gene expression levels, but if you've got 3,000 numbers for each of 700 experiments, starts to be tricky to do it by hand, right? So that's why MATLAB comes useful in this context. Well, so let's see what to do with it. So far we're getting just the numbers that came from experiment. Those are the numbers directly from the table, and depending on the gene, the width of this distribution, width of the range that expression level changes might differ. Some genes might be might change very little from experiment to experiment. Some of them might change more on average. So so we might want to compensate for that before looking at our data. So let's see how to do it. Okay. So a conventional way is to convert the values that we measured into something called the z-score. The way it works is we first calculate for each, let's say, column, the average value that we measured and the standard deviation, how wide the distribution is. That's right. We know how to do it. That's right. We can, let's see, we do have our expression data in ED. That's right. This is our expression data 15215. Okay. How to get an average of the data for each column? There's gonna be average change for a given experiment. Well, what we can do is I'm gonna type it here so I don't lose it. Okay, I'm gonna do control. I'm gonna make myself a block. And I'm gonna try. Well, I want to get expression average. Well, what I do is I'm gonna say that I want a mean. That's how this is how MATLAB deals with gets the average. Okay, we want to get an average for our ED. This is where our expression data is sitting. Okay, but we've got to make sure we're getting the average for each column, not for each row. Okay. You might or might not remember what the mean is returning, but if you don't, you can always run it. You can always feed it with just your array. Okay, run it. Okay, we should have now the average variable, and we check the dimension. We ended up with 136 numbers. So apparently we average across columns, right? Because we had 136 columns, well, across rows, because we had 136 columns with 3,000 or so data points. So if this thing collapsed to a list of 300 or 136 numbers, it's got to be averaging along each column. So we are fine. So this is our mean for each column. How to get a width? Well, the same way we'd say E STD, okay, STD, okay, and then it's gonna be now S standard deviation. That's how MATLAB is getting standard deviation. We're getting also in the, and we'll rerun it. Now we should have ESTD. Also the correct dimension. We've got 136 values, one for each column. If we want, as a reminder, to change the averaging, instead of averaging along columns, if we want to average along rows, then we do EAVG, and then we look for a mean, and we've got to have a mean of AD, but we've got to specify we want, and notice, I mean, MATLAB is telling us that we've got to specify which dimension we want to do. Well, and we want to do second dimension, which means columns. So this is going to be our average across rows. So this is going to be the average row. Let's call it this way. And if we want to get ESTD row, how we vary across the rows, it's going to be STD ED also second dimension. Okay, so if we now run this snippet of code, I've got STD. Well, STD doesn't like me. Why is this? Well, let's see. Well, with standard deviation, there's one more parameter if you want to specify the column. It has to do with the way standard deviation is calculated. You can calculate it by dividing by either the number of data points or number of data points less one. It depends. It depends if it's standard deviation of entire data or just of a sample. If it's sample, then you're doing n-1. So that's what we want. So we can specify, I think, 1, and then we specify we want to go across 2. And now it should work. Yep, now it works. Now we've got ESTDR somewhere here, and this is 3,000 values, because this is one value per gene, and it's standard deviation across all the 130 or so experiments. So that's why the R version here and here it's 3,000 or so wide, because it's going averaging across the columns. But we're interested in the things without R. Okay, so now we can look at one of those into AVG, and let's look at, let's say 1 to 10 positions. Okay, if we check what's there, well, there are some average values there. Looking at numbers, not informative, so we can always look at the histogram of this, right? We can we can do histogram of EAVG. Okay. Let's see if I made the type or not. No, so here. Okay, so this is the average change in expression level across for each experiment, right? And it's on average not much happens. There are few cases where you're getting expression going up on average, but most of the average expression doesn't change. This is for across all the experiments. What about standard deviation? What about variability? The same thing. We can either look at it as numbers, just say ESTD, okay, and we're getting a bunch of numbers, or what's more informative, we can go and do histogram ESTD. Okay, and this appeared out somewhere here. So now you see that there's more variability. There's a lot of data sets where the change is somewhere on the order of somewhere around 0.1, 0.1/2, but there are data sets that are much more variable, they're much more spread out. So this way you're starting to pull in differences between different experiments. Okay, if we want to put everything on the same scale, so that the change for a given change it means the same for each experiment. One way to do it is to just calculate a z-score, which is the value of expression in a given experiment, then we subtract the average, so we bring everything to 0, okay, and then we look how much different expression is from the average for a given experiment, and then we divide the difference by the average spread, and this way we normalize it across all the experiments. Okay, so let's do it. We did calculate the average in ESTD, so our expression is sitting in ED, okay. Our average values are sitting in EAVG, we're fine. And we're dividing by the standard deviation for a given experiment. Okay, this is our Z. So then I'm gonna put a break here. Okay, and let's run this thing. Okay. Thing to notice is I've got to divide on a element by element basis. I can't divide by as a matrix operation, because this is not what I want. I want to take, let's say, expression data sitting at the position 1, 1, absolute value. I want to subtract from that the average value for a given experiment, for a given data set, and then divide it by standard deviation. So that's not the operation done on as by matrix. Let's see if that's the case. So, well, let's do it piecewise. Okay, let's try first. Let's see. So let's see what happens if I do ED minus EAVG. Okay, let's put it somewhere. Let's say put it into X and see what's here. Well, our PD. Now we're getting let's see how it okay, so this is our difference. Okay, so let's try what's there. Histogram, and let's try X at position. Let's say take entire column, but let's try first column and see what happens. Okay, this didn't change much because we're starting from a data that was centered roughly about 0, so we can't see if we're doing fine or not. But we can continue on, and then we can instead of getting just the difference divided by the standard deviation that we get in ESTD, and we've got to remember that we've got to divide it by as a scalar operation, as a matrix by position. Okay, if we do this, and now let's see what do we have in X. Okay, now this thing starts to look like a normal distribution. It's roughly 1 unit wide. That's right. You can contrast it. You can contrast it to whatever we had before. Let's recalculate X this way versus this is gonna be our Z. Okay, so doing it this way. Okay, so we started. Okay, so we've started with histogram of ED, which is first column. This is our starting point. Okay, we're going between minus 0.2, 0.2, something like that. Okay, and we seem to be centered, although it's not clear. This value is, yeah, we're roughly centered. Okay, but now if we now plot our X, which is subtracting the average from each distribution, we're gonna get something similar, because there was no change for this particular experiment. There was no change. But now if we go further and plot the Z, which is our center data divided by standard deviation, now what we average standard deviation, what we do get is now something which is roughly, if you look at this thing, it's roughly 1 unit wide. So we normalized the bulk of the measurements to a normal distribution. The outliers now are scaled in the same way for experiment 1 versus experiment, let's say 2. Here's experiment number 2. That's right, it's same thing, except now there's outliers somewhere here, even farther out, but bulk of the data falls between the -1, 1 range or -2, 2 range, or more or less. So So this way, we have no problems comparing individual experiments, looking for outliers or things that stick out from the from non-interesting cases. So that's a typical way to normalize and convert data to look at different experiments. We're just trying to see how to compare experiments with that in raw data look quite different. Okay, so let's. So okay, so what we've seen, let's get back. So let me do it in the script so that we've got everything here. This is the same thing as what we had before. Okay, I'll rerun this, and then let's put a break here. Okay, and can't use this one in -5, let's say. So control escape. So here's another case. Here's a case of a data where outliers are mostly on the negative side. So it means that for this particular experiment where you knocked out one of the genes, most of the changes correspond to some of the gene expressions going down. There's not much things. This is different than the first two, where there was a lot of things on the right side of the plot. Okay, so question is this thing a really normal distribution or not? Right? How to check it? Well, we do have for each experiment, we do have the average value. We do have standard deviation. That's what we got. That's what we calculated here. That's right. We've got the average value. This is for each experiment. We've got the standard deviation for each experiment. So we can calculate how the normal distribution with those parameters would look like. That's right. We can generate the Gaussian with the proper parameters. Okay. And it's easy. We can just use a function called norm PDF. This is normal distribution. We're gonna plot it as a probability distribution function so that we can compare it to a histogram that's plotted in the same way. Okay, and we're gonna pick up some sensible range for our distribution. To do this thing, we've first got to look at one of those. Okay, I was plotting before 5, so let's check what the 5 does. Okay, this is 5th column with the 5th experiment. Okay, we're getting let's see. No, we're gonna do it a different way. So no, we're gonna do it a different way. Okay, so okay, let's go back here. So let's go back here, and here's our histogram for the 5th column, corresponding to 5th experiment. Okay, let's go here. That's okay. Well, is it normal distribution? Well, if it is, then it would have a width of 1 and would be centered on 0. Okay, let's see if our guess is correct. We can plot. Well, we can decide first. We can decide on the range. Okay, we'd like to. Well, So go back here. Okay, let's go back here. Okay. So we'd like to plot our normal distribution between let's say -12 or so and 4, maybe 6. Okay, 15 to 5. Okay, so to do this thing is we'll need to create a range of values to plot things. So let's say our range is gonna be between -15, let's say, and let's say let's make it 10, but we want to step more often than 1, so we're gonna set an interval of, let's say, 0.2. Okay, this is gonna put a series of numbers into R starting from -15, then 14.8, and then so forth down up to 10. Okay, so this is our range of values, and then to calculate the height of the normal distribution, we'll use the function here. Okay, let's copy and paste it here. Okay, we've got to feed it with the right parameters. This is gonna be our normal. Let's see the norm. Okay, we're gonna specify that our range is in R. Okay, we can explicitly specify it here, but why not? And if our normalization is fine, the mean value should be 0 and standard deviation should be 1. Okay, so if we run this snippet of code, we're gonna see the histogram for our 5th column, whatever is there, and then we're gonna so far plot. Let's move it to this thing here. I want to move it here. Okay, we're gonna normalize histogram to probability density. This is the same scale as the function here is using. If we plot histogram this time of control, well, so now we'd like to plot our R as X value and our D norm as Y value. Okay, this is plotting histogram of whatever is sitting in Z, and then we'd like to also plot there our expected normal distribution generated with binorm PDF. If we run it, if we run it here,
it works very well.
suddenly we see only normal distribution. We don't see the histogram. The reason is that if we're plotting consecutive things, okay, generating consecutive plots, the next operation erases the previous one. So we plotted histogram, but then directly after that we plotted an XY plot, and this one removed histogram. To retain the histogram while plotting on top of it something else, we've got to say that we do hold on to our previous plot. Okay, now what happens is if we run our snippet of code, now we see both lines. Okay, we plotted histogram, we hold on to it, and then on top of it, we plotted our expected distribution. Okay. If we now keep plotting something else, let's say we try histogram of, let's say, Z, but now we're gonna pick up, let's say, sixth column. Okay, this is same as here by this. We pick up sixth column. If we do this thing, now if we do this thing, if we do Control Enter, now there's a typo. That would help. If we plot those things now, it's still not what we want, because now when we run three things in the series, this hold was still in effect. So we plotted once more the histogram for fifth thing, then plot for it, then so we're starting to stack things on top of each other. So thing to remember is that before and after generating stacked graphs, we've got to actually make sure that we do have hold set to off. Okay, this makes sure that what we're doing after that is gonna clean the plot, clean the figure. Then we plot our first histogram, then you hold on to it, and then we plot the line, and then we've got to say hold off. Okay, and this way, if we surround all the graph operations with hold off, so we're not going to have a problem that there was something before there that we didn't want to plot on top of that, but we want to start from scratch. So this is a sensible practice to start with hold off, then plot your histogram, and then hold on if you want to overlay stuff, and then once you're done, you can overlay obviously more things. Then at the very end you hold off to make sure that you're done with overwriting things. And now we can run Control backspace, Control Enter here, and we've got the fifth experiment overlaid with the normal distribution. And then if we want to change to a sixth data set, we can rerun it. And we're gonna have a different distribution here, presumably. Let's see. Is it true? Okay, it's 596 here, and now if we rerun it for, let's say, column number 5, if we rerun this thing and see what's here, now it's clearly different. We're plotting different things. If we want to, we can try to see if it's really the case by actually plotting Control C and Control D, and we can Control D and plot stack two histograms on top of each other, and then plot the normal distribution. And if we do it this way, we should see, well, this one is apparently overtaking the other one. So we can't tell if there are two, but we can try. We can try, for example, we can try to shift one of the histograms sideways, right? We can subtract, let's say, 1 from this guy, Control Enter, It's nothing there. Why is it home now? Hold on. Oh, that's strange. Oh, because that's the problem. Probably. No, here's the problem. Isn't it? No. It's weird. It can't overlay. Well, maybe histograms can't be overlaid. Okay, we'll investigate later. But anyway, here we should be able to over at least plot with the histogram. Okay, so so that's how to overlay curves. Let's break for a moment, and let's continue in five minutes. Okay, stop recording. Oh, no, cancel. Are you sure? Stop. Cancel. We want to break. No. Zoom record. Keep going. Okay, so now let's go back to our histogram with the overlaid normal distribution. Okay, so this looks like it might be normal distribution, but we're not sure. It's not exactly how we would expect the histogram look relative to our normal distribution. Maybe we're off with parameters. Maybe something. Maybe this is normal distribution, but slightly narrower. We don't know. Okay, we can try to fit normal distribution as well as possible to histogram. It's relatively easy. What we do is we just call a function called norm fit. It will take a series of data, let's say in our column 5, okay, and we'll try to find best parameters for a normal distribution that would correspond to the data that we collected in data series, okay? The function is gonna return standard, the mean and standard or average value and standard deviation for the width of the distribution. And then as before, we can use those two numbers to generate the fitted normal distribution and see if it looks better, right? To do this thing is we're gonna run our norm fit, okay, on the 5th column as before. Okay, this is gonna generate us, give us the mean and standard deviation of supposedly normal distribution corresponding to our data. And then we're gonna reuse our range from here that we used before. We're gonna, instead of this thing, okay, this is for a different data set, we're gonna reuse the range here. Okay, this is the same as we had before up here. We're gonna use the supposedly better values of the mean and standard deviation, and let's try to plot it on top of whatever we already have. That's right, we've got the plot here, so let's add another XY plot. So we're gonna get rid of this hold here, so that hold we're gonna keep holding to whatever we've got here. And well, we can't get rid of, we've got to say before plotting, we want to do hold on. This way we're gonna X, and here we're gonna control V. No, what did I do? One moment. What did I do? No, it goes out. I want to do hold on and the fit, and then plot our fit. I think this is correct. And then hold. Oh, okay, here's how the here. Okay, let's try it here. Okay, control enter. Error line. There's a problem, line 41. Oh, we don't have the range. We got to use our R here. R here. Let's see if this one is better. No errors at least. And not going to hold. I'm gonna do hold. Oh, but I've got hold on here. Hold on. Okay, so I'm losing track of what's happening. Okay, so okay. So we plotted here the fifth histogram. We plotted on top of this thing normal with distribution. Okay, now here we want to get rid of this thing. Now we generated a fitted version of the normal. Okay, we calculated the numbers here. Now we've got to do hold on here, and then plot it, and then do hold off. Okay, let's see if it works. So let's kill the, oh no, it's the finger. Okay, histogram is gone. So let's rerun this part. Okay, no, it's going on the control here. Where's my plot? Let's see. Here I'm losing track. Okay, hold off. Okay, this should work. Doesn't. Where's my something's bad happening. I'm losing. And let's clear this. No, I don't want it. Let's run here. Do we have a? I think the laptop is acting up. Something's bad happening. Okay, let's control here. Oh well, let's clean up and reset everything to This is no, we've got okay. Oh, yeah, okay, here. Okay, I think we're back to where we should be. Okay, so I think there's something happening. Okay, let's go back. So let's run here. Okay, so here's our first histogram and then normal. Okay, so now we generate fitted normal. We plot it here. Let's try to see all the, oh, that's the problem. Okay, and now try it here and see what do we have here. Well, we do have the right stuff, but I zoom in. Yes, I can. Well, if we can't see it on a plot, we can always check what this z mean. Okay. Well, it's close to 0. What about standard deviation, ZSTD? Well, it's close to 1. So this thing generated control C, control V. Yeah, it's so apparently this is the best we can do. That's how it looks like. There's no way to get a normal distribution fitted to our data. So conclusion is this is likely not a normal distribution. It's biology is not run by mathematicians, so the fit is not that good. Okay, let's see. So this was more or less demonstrating how to overlay two different types of plots within one figure, let's say histogram and the line plot. We might also want to see several plots on the same figure. That's right. We may want to show histograms for 2 or 3 separate data sets. This is a different way of combining graphical data, and this can be done in a slightly different way. We first specify that we want to plot a figure, let's say 1. There can be more of those. I think this is optional, so we're gonna comment this thing out. Okay, we're gonna make sure that we do hold off, and we specify that we want to generate the subplot. Okay, we're gonna have over all 4 of those. We're gonna have 2 rows. We're gonna have 2 rows and 2 columns of plots, and then for the figure number 1. We're gonna plot histogram from, let's say, at position, that's position 1. Okay. For plot number 2, which is gonna be first row, second column, we're gonna plot data set from the column number 2, and same thing for the other 2. We're gonna go to data set number 3 and then data set number 4. Okay, when we run this, okay, and everything's coming. We do control here. Now we've got four data sets. That's right. This is first one, second one, third one, fourth one. They are not shown in the same way because each one do have outliers in slightly different ways. So this shifts them around the horizontal axis. They are also normalized to count. So this is not how we want to look like. Well, we can fix this thing and make it looks better. It's sort of tedious, but doable. We've got histogram here. So now we've got to well, let's try it. Let's try it first here. Okay, let's for each, let's generate a normal distribution for each of those. Okay, let's try. Let's go back. Well, first we have to oh, okay. So let's do it in a way where we don't have. Well, we can do it in a tedious way. We can plot all those four histograms in a tedious way by cutting and pasting bunch of parameters for each histogram. But we can do it better. Okay, let's start the block. Here. Okay, shift. Okay, and let's do the following. Okay, let's do hold. Okay. Off. Okay. Okay. Then let's decide we want to have four things. So let's do for plot 1 to 4. So we're gonna repeat the block of code between 4 and we're gonna repeat it 4 times. Okay. For each pass, we want to generate a subplot. This is gonna be subplots in a 2x2 grid. The number is gonna be pp. Okay, so this is gonna generate us consecutive subplots. In each subplot, we want to generate a histogram. Let's say histogram. Okay, it's gonna be histogram of our normalized, or let's of our normalized data. So let's say the column pp. So it's gonna be column first, second, third, and fourth. Okay. That's what we need here. Okay. We've got to hold on to this histogram to modify its properties. So we will hold on to it by assigning whatever it returns to h. Okay. Now, as before, we've got to say h normalization, and we're gonna normalize to PDF. Okay, so this is gonna normalize our histogram, and then we do have somewhere before our normal distribution, somewhere here. Have it somewhere here. Here, that's what we want. Control E, then we go here. We're gonna calculate it. Control V. So here we specify the range from, let's say, -15. Let's make it symmetric. Let's make it to 15. So we're gonna, in D norm, put the normal distribution between -15 and 15 for the standard deviation 1 and 0 average. Okay, and then we're gonna plot it. So we're gonna plot. Plot R is our X range. Okay, our Y is D norm. Okay, so this is what we're gonna plot here. Hopefully, oh, and I've got the missing bracket here. Okay. Okay, and then we're gonna go here and do hold off here. Hold off. Okay, so this way we're doing 4 passes. For each one, we're plotting one of the data sets in a separate plot, and then we're overlaying it with the normal distribution that we see. We're trying to see if it corresponds to our data or not. Let's run it. And what do we have here? We've got things here fine, but where's our data? Well, we didn't hold on to the histogram, and that's why the histogram is gone. What we've got to remember is that is this what happened? What in the world? Please don't tell me. Did I lose my test? What happened? Did I wipe out my? That's bad. Oh, okay. Save us. Okay, this thing is acting up. Okay, I'm gonna stop recording and recover because we've got the technical problem. Okay, let's resume. Okay, so let's try to recover. I think my laptop is acting up. So let's go where we were before. Okay, we've got to reread our data here. Control Enter. Okay, here's our data. Now we're going to calculate the averages and standard deviations. Okay. Oh, because we didn't run a snippet here. We need to we need to run this thing here. Control here. Okay, here we've got. Here we should have. Now we should have averages. Okay, is okay. We do have averages. Right. Okay, so we do have stuff that we want to. Now we're gonna get the values. Okay. Here's our single data set overlaid with the normal. Okay. And we should see yeah, here it is. Okay. This is fine. This is when there's a typo here. Okay. And now let's see what do we have here. And this is what I was trying to modify. Okay, so let's quickly rewrite this thing. Okay, so we want to hold off. This is gonna make hold off. This is gonna make sure we're erasing everything. Now for plot 1 to 4, okay, we're gonna do it here. We're gonna do subplot. It's gonna be 2 columns, 2 rows, and first position. Okay, we're gonna do H is histogram. We want to histogram. We want to plot Z at position PP. So this is first experiment. Okay, for H we want to normalization. No, the normalization. We want to set it to PDF. Okay, so this takes care of scaling it right. Now we want to hold on, and we want to plot, and we'll have to generate what is gonna be R to generate our normal thing. We'll have to go up here. We want to generate our normal here. Control C, and then here Control E. We want to cover a range from -15, let's say, to 15. Okay, we're generating normalized to PDF, and we plot R versus the norm. Okay. And then once we're done, we do hold off. Okay. So let's put end of the section here. Let's see what happens here. Well, I'm gonna do save this thing just in case. Let's control enter this thing to This is strange. Oh, because hold on. Something bad happened. Is it not for the histogram Z? Okay. Normalization, hold on. Oh, because I don't go over the plots, so I overlay them in place. Okay, let's try it now. Control Enter. Ah, here it is. It's better. -20. Well, this is sort of better, but one of them has outliers at -30. No. This way. That's weird. C H on this should work. H. Well, it's interesting. If I change R to minus. Okay, let's get. Let's resign from overlaying stuff with plots. We'll investigate it later. Okay, control, and let's rerun it. Rerun it here. Okay. Okay, so here at least we've got histograms here. Okay, so we can clearly plot more than one thing, one XY plot in a figure, but it's sort of tedious and repetitive to do it. So let's try to avoid writing this thing over and over again and rewriting it all the time. Let's try to make it more universal by converting this snippet of code to a function. What we'd like to do is we'd like to say something like plot maybe plot 4. Okay, we'd like to specify let's say our data, which would be, let's say Z. This is where our data lives. We will specify as a list which data sets we want to get. Let's say first, second, third, and fourth. Okay, and we'd like to use this thing every time you want to plot a panel like you've seen with four XY plots at the time. Okay. Well, how to do it? We'll make a new file. Okay. We're gonna take the code we've got here. Okay. And we'll paste it into our file. Okay, and then we'll try to make a function out of it. Okay, how to do it? We're gonna say function. Target function. It's function. Okay. Now it's supposed to return something, so let's do ret something, and then the name is gonna be plot 4. This is what we want to do here. Okay, we're gonna name it plot for. Okay, and the arguments will be our data set, and it's gonna be pos, a variable which is gonna be a list of pos is bad. Okay, let's do call. Okay, that's mean columns that we want to plot from the data set. Okay, so now we'll pre-calculate as before our range. Well, okay, let's get rid of it. We're not using this thing. Let's get rid of this. We're gonna at the beginning hold to well, that's how it goes. Okay, we hold to off. Then we're gonna go over 4 positions. Okay, subplot stays as it should be. But then we're gonna take data from DTS here, from DTS. We're gonna use a column, but at position that's coming from call. So we've got to say we want to use call PP. That's right. This is gonna be going from first, second, third, and fourth in here. Do we have the right number of brackets here? Call here data set. Okay, we close data set, and then we close histogram and column. Okay, we've got to normalize to PDF here. Okay, we don't care about holds. Okay, and okay, and then at the very end is off, and here at the very end we should say end to end the function. Okay, good. Okay, so this is our function, and then we've got to save it in a file with the same name as we use for the function name. So let's save as MATLAB knows it's supposed to be called plot4. It goes to wherever is our current directory, so we save it here. Okay, so this is hopefully our function that we call like here. We just call it plot4, and then we specify our data, which is sitting in Z. We specify 4 columns, and then if we run it, hopefully, we've got 4 data sets that we're interested in. Okay, if we want to plot a different data sets, we can now just specify here that we want, let's say, column 11, 12, 23, and 44. And then when we run it, here are different assets that got plotted. So this way we save ourselves typing this, right? Because instead of writing things explicitly, we can write a universal function that does things for us, and then we just pass parameters, and different things are plotted in a way that we defined in a file here. So that's how writing functions in MATLAB looks like, and this is done to avoid repetitive typing scripts and copying and pasting. This is something that can be used over and over and over again. We can modify the contents here to plot things in a nicer way. That's right. And we're also reusing pieces of code here by using the for loop. Here looping is not a problem. There's no built-in functions that let you generate all those plots with iterating over data sets explicitly. So we've got to actually do the looping on our own. So here the use of for loops is perfectly fine. It's not limitation. It's not the speed of calculation limitation. It's probably graphics that was playing things. So we're fine here. Okay. So that's how functions look like. Okay. Another place where functions might be useful is when you're generating test data or things like we did at the very beginning or and yesterday. That's right. To generate our test data here, we run a loop to generate our test data, then we save that. Okay, and then if we want to generate things in a similar way for different testing different scripts or whatever, we can put it into a function. It's pretty simple, the same thing as before, except that in this case here we didn't return anything. There's a return value specified in a function definition, but we don't assign anything to the red variable, so nothing is returned. With the function that generates data, we can actually return the data itself. Okay, so let's get this snippet of code first and copy it into our new file. Okay, and now we want to make a function out of it. So let's make a function out of it. Okay, let's make a function. It's gonna return something. Let's call it my test data. Okay, we want to generate n rows of data. Okay, so this is gonna be our 1000 original case, but we'll be able to vary the number at will. Let's say n calls. This is gonna be number of columns, and we can specify that for each column will have a specific standard deviation for the normal, and then let's say another parameter we can shift it left and right, so change the mean. So we'll need a data mean, and we'll need data std. Okay, assumption is that those two parameters are lists with enough data enough numbers to generate the proper number of data sets. Okay, so now let's remove this thing. We don't need it here. Okay, so now what we need to do is, okay, first we've got to make space for all of our data. So let's say that our red is initially full of zeros. Okay, and we need n rows of zeros. This is gonna be coming from here, and rows. Okay, and we'll need n columns and calls. That's right. So this is making us space for storing data that we're generating here. Okay, we're gonna go over columns, but this is not n call. This is gonna be n calls here. So that to be different variable. and calls. Okay, so we're going over columns. Okay, for each column, we're gonna generate a ret. Okay, ret. We're gonna generate entire column, so all the rows, all the values in a given column. Okay, this is gonna be column CC. Okay, it's gonna vary from 1 up to n calls, and we're gonna take the standard deviation from DSTD, from DSTD. Okay, this is with assumption that DSTD is a list or with enough values. Okay, I'm gonna generate the random numbers with number of rows coming from here. So this is how many data is going to be generated there. And this is so far normal. This is so far random variable coming, or series of numbers coming from random, from normal distribution, width of 1 and mean of 0. To shift it to the mean we've got here, we've got to just add the mean at position corresponding to the row, so to CC. Okay, so this way, in this way, our loop is filling our initially array full of zeros with the values coming from normal distributions. Okay, and then that's about it. We can say, and we should be able to save this thing as my test data. Save as my test data, and I'm gonna call it 2 because I've got a file called test data to here. So let's save it here. Okay, it's probably the name's got to match the name of the function, so save it once more. Okay, now we're fine. Okay, but so far we just generated the data. We want to save it. Why not? So we can pass another argument, which is gonna be the file name. Here, let's say f name. Okay, now we're gonna use it to open the file with the f name. Okay, we're gonna open this file for writing. That's fine. Okay, this is as yesterday. We're gonna now go over our ret variables. So we've got to change size, check size to ret. Okay, same thing here. So here we're going over rows. Now we're going over columns of the same variable. Okay, and now we want to print out the values. Okay, ret, and then after printing the values across one row, we want to put the new line, and then at the very end we want to close everything. And now let's save. Okay, so we've got another function. Does it work? The difference between the function here is that here we don't return anything. We specify ret. I think it's redundant. We can get rid of it. I think it's perfectly fine. If function is supposed to plot something but not writing to it, not returning any values, then it's perfectly fine. We're gonna save it here. but the function here is supposed to return the data we generate, apart from besides writing it to a file. So here we specify that the return value is supposed to be stored in a red variable, and we then fill the variable, and then at the very end we're gonna do, and here we are fine with our function. We save, and then let's try to use it. Well, we can go to, let's say, here. Okay, I've got, let's say, a list of mean values, the averages for 1, 2, 3, 4 curves. I've got a list of standard deviations here. So then we can try to call MATLAB data tool. This is how I named the function here. We go back here, and we want to generate, let's say, 100 values per 100 rows. We want 1, 2, 3, well, we want four columns. This is my mean value. This is my standard deviation. This is how we define where the mean and standard deviation is sitting in. Now we go to here. This is going to be test data 3, and then let's see if we run it. We can clean. Oh, no, it's not good here. Let's run this thing here. My test data, we do have error line 65. It waits me. Oh no. Where did I go? Here, 65. What's the problem? My error line 95. Okay, there's an error here. Line 5. What's in line 5? Red CC. Okay. This is fine. Unrecognized n row. Oh, because we've got n rows here, and I've got n row here. Okay, that's better. Let's try to save it and run it. Ah, it's better. So now here's our generated data, and here's our generated file. Okay, we can take it, and as before, we can quickly check what's there. Okay, we click here, and here are our four series of data. That's right. Here's 4 XY plots with 4 data showing up at different heights, because this is the changing. This is the. Oh, no. This is because we started with first series with first series with 0, second with 2, and so forth. So the height of the trace is changing, and also the size of the width is changing. So if we want to change what we're plotting, we can just. If we want to add another one, we can add something, let's say, a standard deviation of 10, and let's say with the mean of 10 and standard deviation of 0.1. Okay, we can add one more trace here. We can generate, let's say, this time 250 points, and then if we run it, and we can say this is test data 4, and if we run this thing, Now we've got 1, 5, 1, 2, 3. No, why we don't have, why do we have only 250? No, it's not. Okay, let's kill it. Let's see what's going on. Control Enter. Let's run it. This is a very unhappy laptop. I'm sorry about this thing, but stupid thing is acting up. This is here, this is fine. And then if we do control, okay, let's clear here, okay, and let's rerun it. No, it's free. It is frozen. It's doing something, but it's essentially frozen. Okay, if that's the case, we'll finish up here because this is not productive. Okay, so far we went through reading data from files containing text, plotting some of those pieces of data either directly as a XY plots or as histograms. We went through pre-processing it by, let's say, converting the raw numbers into z values and then trying to compare or overlay it with the normal distribution or distribution in general that we expect the data looks like. We'll finish up tomorrow with trying to find the interesting pieces of data in the files in a more or less automated way, and we'll try to continue with plotting data maybe in a nicer way, in slightly different way. So that's what's gonna happen tomorrow, and I'm gonna stop recording and hope I'm gonna be able to recover, because I think the laptop is acting up. Let's here. Oh, let's go here and stop recording. Sure, yeah.